goals of the talk, I want to kind of begin with an overview of the GPU pipeline, just to sort of review introduction to graphics. Then I want to move on to explaining forward rendering, explaining deferred rendering, and comparing the two on a sort of technical level. And at the end, I want to discuss where future developments may take us. So to start with an overview of the GPU pipeline, here it is in all its glory. What we're doing is, on each invocation of the pipeline, we send a mesh to be rendered, a mesh of triangles. And this is in the form of a vertex and index buffer. In the input assembler, we assemble these vertices into triangles. In the vertex shader, we transform these triangles. In the rasterizer, we rasterize these triangles into their fragment representation. And then in the fragment shader, we shade each of these fragments, and then hopefully we write the result to the frame buffer. Now, an important thing to understand is that the most expensive part of this pipeline is generally the fragment shader, and this is expensive both for memory accesses and for compute. Typically, we have multiple texture inputs that we sample each one of, large textures, and as well as that, the combination of these texture samples into the final color can be quite computationally expensive. And the particular way in which we combine these samples together is defined by the BRDF, the bidirectional reflectance distribution function. And this essentially defines how light is reflected off an opaque surface. So a particular material will have a particular BRDF. And some examples of these are the Phong model, the Lambertian models, things that we've seen before, but they can be a lot more complicated and computationally expensive than these. So going over what we're actually rendering here, we have a scene, and a scene consists of 3D triangle meshes and lights, and somehow we want to produce a 2D image. One technique to do this is called forward rendering, and this is where we execute our entire pipeline from start to finish in a single pass, once for every mesh light pair. And so what we're doing is, for each object, we are accumulating the effects of each light on it into the frame buffer over multiple draw calls that you can see before, where a draw call is an invocation of the pipeline we saw before. This is called multi-pass forward rendering because we do multiple passes per mesh. Now, this seems perhaps a little bit naive because we're doing a lot of unnecessary draw calls. Imagine we have a mesh and a light separated by a solid wall. That light contributes nothing to that mesh. However, we're still going to go ahead and try and draw it anyway, with the overhead of that unnecessary work. The reason we're doing this way is because in the past we used to have CPU renderers. GPUs are actually a very new thing, and CPU renderers are very slow. And so when we used CPU renderers, we did an awful lot of pre-processing on the scene. For example, binary space partition trees were first implemented in 1993 in Doom. And this let us cull things that we couldn't see, for example. And this minimized the unnecessary work that the CPU renderer did. But suddenly, in 1999, the first GPU came out, the Nvidia Geforce 256. And it was so much more powerful than the CPU renderers that this expensive pre-processing that we were doing on the scenes to minimize the unnecessary work we did was actually more expensive to do than to simply push all of the mesh light pairs onto the GPU to be computed. The reason why they were so fast is kind of explained by this quote from the marketing of the GPU. It was a single chip processor with integrated transform, lighting, triangle setup and clipping, and rendering engines. And that really is all it did. Nowadays, we're spoiled with general purpose unified architectures. We can do GPU compute, we can customize everything. But back in the early mid-2000s, they were heavily fixed function ASICs. and they were fixed function simply to optimize the throughput. And so we had very little programmability and customization. Now, forward rendering also has a lot of natural extensions to it to allow us to model different natural phenomena. One of these is transparent surfaces. To render transparent surfaces, we have something that we've rendered behind it, say an opaque surface, and we have our transparent surface. And this transparent surface, we want it to tint what is behind it. And so what we do, we render all of our opaque meshes. In this scene on the right, you might think, let's say we render the sea and the sky. And then what we do, we render our transparent meshes, the window perhaps. And the transparent surfaces are alpha blended on top of the opaque meshes to tint them, to add grime, as in this image. And so it's a very natural extension. We don't have to do much extra work to get this effect. And there are a lot of natural phenomena that we can model with very natural, easy extensions. So forward rendering, what are the pros and cons of this? The first one is that it's very efficient if we have few lights. For example, imagine a daylight scene. The only light we have is the sun. And in this case, we simply render each mesh once, going through the entire pipeline from beginning to end. It's extremely efficient. As well as this, we can do transparent surfaces very easily. As I said before, it's a very natural, easy extension. One very important benefit is that we can model different meshes with different materials. We can specialize different materials by having different fragment shaders, one for each one, say a fragment shader that does metallics, one that does plastics. When we do a draw call on each mesh light pair, we can specialize which fragment shader we use for that draw call, and thus we can specialize which material, which BRDF we use for each mesh. This seems kind of obvious, but we're going to see why this is important later on. Now, the obvious downside is that as we add lights, the performance decreases rapidly. The number of draw calls is the number of meshes multiplied by the number of lights. And this also, not just having overhead for the GPU, this is overhead for the CPU. We interact with the graphics card through a graphics API. The CPU has to generate these draw calls and has to do an awful lot of work to do so, especially as forward rendering became more and more used, suddenly that overhead became a bigger and bigger part of it. So, an idea. How can we remove this dependence between meshes and lights? In forward rendering, we render every mesh light pair because we need to, and so we generate an awful lot of draw calls. One way we can do this is to take inspiration from something that we already do, and this is the Z buffer. In many games, the Z buffer is pre-computed before the main rendering pass, and this is done so to optimize the main rendering pass. Why don't we do this sort of pre-computation with all the material properties as well as the depth of the fragment? And this leads us to deferred rendering. Deferred rendering splits the traditional pipeline into two stages. The first stage is attribute rendering, and the second stage is shading. In a forward renderer, in the shading step, typically we read from multiple textures, and these samples that we take are the material properties at that point on the surface of the mesh. So we might sample from a normal map, we might sample from a texture map. We take those samples and we combine them into some final color using the BRDF. Let's instead directly write those material attributes that we've sampled into what's called a G buffer. And so this flattens the scene into only what we can see in the same way that shading does, but it does it without the expensive computation of shading. So we have reduced the amount of computation we do up front. However, it's still very memory intensive. We still have to sample these large textures. Now in the second stage, the shading stage, we can do texture reads from each of the images in the G buffer for each pixel. We can then combine these samples using the BRDF and write that to the frame buffer. Why do we do this work? It seems like we've just added something for the sake of it. Well, it's actually quite a big thing. What we've done is we've separated the dependence between meshes and lights. In the attribute rendering stage, we don't have to know about the lights at all. We can simply iterate over the meshes and draw them to the G buffer. And then in the shading stage, we are not referencing the meshes at all. We've compressed all the meshes into the single G buffer. And so we can simply iterate over the lights and compute the contribution of each light to the scene using the information simply in the G buffer. There are some downsides to this. When we compress the entire scene into this G buffer, we lose the ability to keep track of what is behind what. This is fine with opaque surfaces. We can't see through them to see what's behind. But as I said before, transparency requires you to see what's behind. And so we lose the ability to do transparency. As well as this, we have this potentially huge G buffer that we have to move around the device. The G buffer at a minimum contains, let's say, UV coordinates and normals, which lets us sample the textures. But we can really put any material attributes in here. We could store the intrinsic color of the material, you can see on the top there. We can store the depth. We can store specularity and baked ambient occlusion and metallics and all this stuff. And as we add more and more data, more and more information to this G buffer, we have more and more data that we have to move around the device. And so this can really eat up the memory bandwidth. And so here's a sort of representation of the number of draw calls we've sort of optimized to get this. Now, why do we call it deferred rendering? It's kind of a strange name. What we're doing is we are deferring the pixel shading until after we have determined which fragments actually have to be shaded. And this minimizes the number of wasted fragment shades. As I said before, fragment shading is the most expensive part of this pipeline. But this isn't unique to deferred rendering. There are plenty of modifications to forward rendering that have the same benefit of minimizing wasted fragment shades without the whole deferring idea. And the name doesn't actually encapsulate the most important part of deferred rendering to us, that it lets us separate mesh rendering from light rendering to reduce the number of draw calls. And so in that sense, the name is a little bit misleading. Now, this pipeline of the second stage is kind of an overly simple view of what's going on. Older GPUs didn't allow us to go straight from one buffer to another. All we could do is put in triangles to be rendered. We can sample buffers, but we have to start with triangles. And so it actually looks much more like this. Now, there are several ways we can implement this. We can, let's say we have a big light, the sun. The sun affects the entire screen. What we can do is we can put in a pair of triangles that form a quad, and this quad fills the entire screen. When we rasterize this quad and do the shading, we are essentially doing shading on every single pixel of the screen. And then at each fragment, we can sample each of the textures in the G buffer that we need to get the material attributes from, and then compute the resulting color using the BRDF. Now, this works very well if the light fills the entire screen, but let's say we have a very small light that affects only a small part of the screen. Now I'm going to make a kind of assumption here. The smallest light in the world still has a fall off that falls not actually to zero. You could shine a torch 1,000,000 light years away at the Earth, and there is still going to be an infinitesimally small contribution to what you see on the Earth. But that's actually computing that is kind of wasteful. The contribution is so small that you can do without it. And so what we can do is we can model lights to have a fall off that actually falls to zero at some radius. And this lets us restrict the extents of the light. We only have to rasterize, we only have to shade fragments that are that radius away from the light. And this is where triangle fans come in. These triangle fans approximate circles that we center on these small lights. And when we rasterize these triangle fans, only the fragments that are close enough to the light to have some significant contribution are going to be shaded. And so this is a way to minimize the wasted fragment shades. So overall, deferred rendering, what are the pros and cons? The biggest pro is that performance scales linearly with meshes and lights. This is the point of deferred rendering. But there are a lot of downsides to this. We lose the ability to do transparent surfaces. As well as that, moving around this huge G buffer just eats memory bandwidth that we could really use for other things. Oh, I forgot to mention with the benefit of being able to add lights. So we can add lots of lights, and this gives us the artistic freedom to sort of create scenes that we really want. In the past, with forward rendering, we were very limited on the number of lights we could use, thus less artistic freedom. Now, one downside I want to talk about is the idea of having multiple materials. In a forward renderer, as I said, draw calls are done per mesh, and so we can specialize fragment shaders on a per mesh basis. However, in a deferred renderer, we have compressed the scene into the G buffer. We lose the information of which mesh a particular pixel belongs to. And this is the entire point of deferred rendering. We want to be able to do the shading per light, but we've lost the information of which mesh a particular pixel belongs to. We can't run different shaders for different meshes, and so it becomes very difficult to, we have to draw the entire scene using the same BRDF. But there is a way around this. What we can do is we can assign IDs to each material, for example, an 8-bit number. Then in the attribute rendering stage, the first stage, we can store the ID of the material of the mesh we are rendering in the G buffer, as if it were any other material property. What we can then do is we can take all our disparate fragment shaders, one for each material, and we can combine them all into one huge fragment shader. And this fragment shader at the beginning, it samples for the material ID, it finds the material ID, and it branches to the particular BRDF that we want to compute. It computes it and then it returns. And this can be huge. It can branch to as many different branches as you have materials. Now, the idea of combining all your shaders into one with loads of branches sounds horrific for performance. It was basically hammered into us in computer design that you don't do this. But it's not actually that bad. Pixels that are spatially local together are very likely to use the same material as, you render a mesh in a contiguous area. And so we actually make very strong use of spatial locality. So pixels in the same area are likely to make take the exact same path through the fragment shader. I said before that transparency cannot be done in deferred rendering. But there are some cases where it seems to actually be done. GTA 5 uses a deferred renderer. However, it has transparent surfaces. How does it do this? What it does is it renders the entire scene without transparent surfaces using its fancy deferred renderer very quickly. What it then does is it takes the transparent surfaces and it renders those using a separate forward renderer. And it takes the results of those and it actually blends in those rasterized transparent surfaces on top of the frame buffer that we generated before with the deferred renderer. And so this shows us that we can actually mix and match rendering techniques for different materials and lights and meshes within the same renderer. And this is an extremely powerful technique. The vast majority of games use multiple different renderers for different situations, playing to their strengths. And this is something I kind of want to get across, that these different techniques are not things you ascribe to and commit to. These are tools in a toolbox, and you can use multiple of them at the same time. So going back to specifically deferred rendering, when was this developed? It has perhaps humble beginnings. It was first used in the Shrek the video game in 2001. This was developed by, well, the graphics specifically was developed by Rich Geldrick, I think his name is pronounced. At the time, there was no hardware support for this. And so what he did, instead of writing to multiple render targets in a G buffer, what he did was combine the material attributes he needed. He compressed them into the small color frame buffer that you're given, and then he sort of fed that back into the shading stage. After this was released, he continued to work on this. He was involved in a lot of the early research and development of this technique. In 2004, he released the Gladiator demo showcasing his efforts at GDC 2004. And then he joined Microsoft R&D to do a lot of the development of this for the Xbox 360. The first game to be released using deferred rendering after Shrek was Stalker. And from then on, deferred rendering became mainstream in a lot of titles, especially ones that were really pushing the boundaries of performance and what looked good. So from then on, it kind of became standard. But what's happening nowadays? Recently, some high-profile games have been coming out using forward rendering. What's happened? And it's because the situation has changed. Earlier, I described that before GPUs, when we used CPU renderers, we did very heavy pre-processing of the scene to minimize the amount of work that these CPU renderers did. And what we're actually seeing nowadays is the industry moving back towards that, kind of going full circle in a little way. So Doom Eternal in particular uses very, very advanced and heavy pre-processing of geometry and lights in order to cull geometry and lights that we just don't need to draw. And this reduces the amount of data being sent to the GPU for rendering. The reason this change has happened is because the bottleneck has changed. In the past, at the end of forward rendering, deferred rendering was developed because the bottleneck was throughput and the number of draw calls we could make. Nowadays, the bottleneck is memory. Nowadays, draw calls are cheaper than ever with the introduction, especially of very low overhead graphics APIs, for example, DirectX 12 and Vulkan. The CPU can generate many more draw calls than it could before. We're finding that forward rendering with very heavy pre-processing of the geometry is just as fast as deferred rendering, if not faster. And as well as that, it has much lighter burden on memory. because deferred rendering needs to move around that G buffer. Now, what do I mean specifically when I say memory bottleneck? I mean two things. There's the CPU to GPU bottleneck and the GPU internal bottleneck. Now, when sending data from CPU memory to GPU memory, we send it over the PCIe bus. And this data is typically mesh and texture data. Remember that textures are attached to meshes. The other bottleneck is moving data around internally on the GPU. Now, a lot of this happens implicitly in the background, so it's quite hard to control. For example, having a large G buffer, we both write to that G buffer in attribute rendering and we sample from it, and so we convert between those two representations, and that can be quite expensive. To help with the first bottleneck, we want to minimize the amount of geometry and texture data being sent over the bus. Now, deferred doesn't actually help with this because we send every mesh to be rendered with both traditional forward and deferred rendering. And so this is why we do the pre-processing. We cull the unnecessary mesh-like pairs being drawn so that we don't have to send as much over, and this reduces the load on the PCIe bus. The second bottleneck has become an issue because we're using larger and larger textures. We really don't need this huge G buffer taking up our quickly diminishing memory bandwidth. And so a lot of games are now doing this pre-processing before forward rendering. So what are the key takeaways? Deferred rendering was really a response to the bottlenecks of the time, and that is seen in all of the sort of radical new ideas that we see in rendering. Nowadays, we're moving back towards heavily pre-processing our scene, similar to what we did in the 70s, 80s, and 90s. And so in the future, things are going to change, the bottlenecks are going to change, and I'm afraid we're probably going to be doing a lot of reading decades-old papers on ideas that have suddenly become relevant again. And so here are my sources. These are all great reads. I'd highly recommend having a look at some of them. I'm not biased at all. And thank you for listening.